Okay, so let me grab my calculator quick. Today, just to follow up to the activities we did today. So remember, the only thing before today that our kids had discovered is that if you have, say, tiles and you have 3 by 4, that you can multiply because you have 3 groups of 4 to get the area. So 3 times 4 is whatever, 12, say, square centimeters, because we're literally counting squares. And then the perimeter is just all the sides added up. And again, if they want to be more creative than that and create a formula that's a little more complex, that's fine. But 4 plus 3 plus 4 plus 3 is what? 7, 14 centimeters. And again, those are like people sitting on the side. So they don't take up any space. They're not squares. They're just lengths. So it's like string getting pulled all the way around here, and then I would actually measure the string, which would probably be something I would have kids do. I would put the tiles and then have them, take the string, work with a partner, and then literally measure the string to make sure that works. So everything that we know has to be based on this knowledge, because we don't know anything else. We only know, as far as area, rectangles and squares. So today, in class, when we did the dot board or whatever, the dot paper and the geo board online, is if we have a triangle that's a right triangle, that's not too hard for kids to see. They can double it. And so then they're like, oh, well, a triangle is half a square, half a rectangle, so that makes sense. But if the triangle is not a right triangle, then it gets a little more complex. And I'm going to go grab my blue marker here. Sorry. And so here, but they can use that same idea because they know that a parallelogram also has the same formula as rectangle. So they could double it. So again, you kind of have to copy it and rotate it a little bit. And then what they could do is they can cut off this end again and then glue it in here and get back to a rectangle. Or they know that a parallelogram is the same anyway. So then they're like, oh, so that would be base times height, but I'd have to divide it by 2 because I made the area twice as big. And then some of you had the great idea in class of, if I had a triangle, say like this, again, not a right triangle, or at least not supposed to be. A lot of you are like, well, could I go ahead and fill in that rectangle and then kind of realize that these guys are going to have the same area, and so are those two. So I still have half of the space filled up, and a rectangle has a formula base times height, and I have half of that. So both those methods kind of lean nicely to why you take half base times height. Base times height is your rectangle, or base times height is your parallelogram. So say like this, and then you double it, and you have that. So those work really nicely. And I don't know that you would have figured those ideas out without the dot paper. Maybe this one, but this one I'm not so sure about. So again, having that dot paper helps you kind of see the grid and see the squares and try to think about how you can do that. And then the other one that we did in class was, again, say I have this triangle, that we could kind of cut this piece off at the halfway mark. So if this is my height, right, I take that off, and then I can move it and kind of put it in this space. And I can get a parallelogram, which again is base times height. But again, the problem with base times height is I don't really have the whole height. I only really have half the original height because, if this used to be 4, now it's only 2. And so all of those explain why triangles for area have the half base times height. And again, if students want to write that base times height and divide by 2, or if they want to write base times height and divide by 2, that doesn't matter so much to me. I just want them to conceptually understand why a triangle is half of a rectangle, half of a square, or half of a parallelogram. And again, the reason I call these TRs is because really they have the same formula. Trapezoids and triangles both start with TR, and this is half big base times height. So they're really the same formula, except triangles only have 1 base and trapezoids have 2 bases. But again, if you want to remember base 1 plus base 2 times height, you can do that as well. But I found, at least with my students, just getting the fact that they're going to both be half base times height, either base or bases plural, that kind of, again, minimized how much they had to know here. So let's look at trapezoids. So a trapezoid, one way you guys talked about in class is, again, breaking it into things you know. And at this point, we had already discovered this, and we had discovered this. So a lot of you are like, well, can we just do this and add up, you know, triangle number 1 plus the rectangle and then triangle number 2, and just find the area by using base times height for this guy, and half base times height for that one, and then half base times height for that one? And the answer is yeah. So on a test, if you wanted to do a rectangle plus the area of triangle 1 and the area of triangle 2, and add those all up, absolutely. I would totally count that right. It works, and it's a great strategy. If we want to get to the formula, then we're going to kind of use that same idea we did with triangles. So if this is my trapezoid, and remember trapezoids have 2 parallel sides, then what I'm going to do is copy this, and I'm actually going to flip this side and put it up here, and flip this side and go down here. So for example, if this is 7, this is going to be 7. If this was, say, I don't know, 4, this would be 4. And again, I'm not very good at drawing, so it looked much better on the computer. And so really, this is what I want to find the area of, but I really doubled it. I made a replica of it, and so I have to figure out the area of this new parallelogram. Well, parallelograms have the formula base times height, which we know from the other day. So my base is now 11, though, and my height, I don't know, pretend the height is 2. So the height is 2. And that would be 22. But again, I doubled this. And so to compensate, I have to go back and take half that. So half of 22 is 11. And again, this would be what? Square centimeters or square units, because it's only half. So you can kind of see the idea that a trapezoid is the exact same idea as a triangle, as far as the method where you double, and then you only take half of it because you really don't have a parallelogram. And so you really want to take half of it. The only issue is you add up the bases, the 4 and the 7, because when you flip it over, that becomes your new base. And again, if you prefer base 1 plus base 2 times height, that works. But they're really the same idea, all right? And then as far as perimeter, on a triangle, you would just add up the sides. And on a trapezoid, you could just add up the sides. So adding up the sides always work. Now, again, you might have to do Pythagorean theorem or something like that to get the side length, especially if we're dealing with dot paper. So if you have a triangle like this, right, and you want this side, you might have to kind of come over here, draw a right triangle, and do Pythagorean theorem to get this side. And then let's see, this side you're probably going to know, so maybe this is like 6 inches or something like that. And then this side, same thing, you might have to, you know, get a right triangle and do Pythagorean theorem to get that side. So you might need to use Pythagorean theorem if the numbers are not given to you. All right, so we only have one shape left, and we will do that tomorrow, and that is circles. And if you know these 3 categories, yeah, you can pretty much do anything. So we will talk about circles tomorrow, and then we'll practice some just finding areas of weird shapes, normal shapes, and things like that. All right. Have a good one.